Hello everyone, welcome to the course on digital communications. In this course, we will see what happens inside a digital communication system. Let us first see what is the purpose of any communication system. The purpose of any communication system is to transmit some signal which is generated by a source to a destination through a media or channel. So, there is a source which is generating some electrical signal which is possibly captured from some real life image or audio, and then the signal is generated by a transducer, and then that needs to be transmitted to a destination through a media which is technically called the channel. So, we have a source, a destination and a channel. So, let us see some examples. Radio is a very common example. The source in this case is a microphone which captures a signal from reality and then converts it to an electrical signal, and then that needs to be transmitted through space, and it should reach the destination and should be reproduced at the radio receivers at the user's place. The next example is a similar example, television, where the source and destination are similar, except that in this case we are dealing with video instead of audio signals, and the source of the electrical signal is the video camera and microphone, because there is video as well as audio signal, and then the media is again the space, and the destination is a TV set which has a picture tube which should display the video that was captured by the video camera, and the speakers in the radio TV receivers which should reproduce the sound that was captured by the microphone. The next example is a telephone system where the source is the microphone in a phone set and the destination is the speaker in another phone set, and the media in this case is wire line, the twisted pair wire. In the next example, we have again a telephone, but it is a cellular mobile phone, and the channel in this case is space, unlike the twisted wire in the case of telephone, traditional telephone. So, in this case again the source is a microphone in the phone set and the destination is a speaker in the phone set, another phone set. There are some not so obvious type of channels other than what we have considered. For example, what are known as storage channels like CD, magnetic disc, magnetic tape, etc. So, these, though they do not seem like channels, actually they also can be considered a channel, and when you are writing on a CD or recording in a magnetic tape, that can be considered as that we are transmitting some signal, and then when the time progresses, the tape or the CD may be damaged in the due to some phenomenon, like there may be a scratch on the CD, there may be some magnetic interference in the tape and the magnetization may change in the course of time, and as a result when we play it back we may not receive the same signal as it was recorded. So, this writing on a CD and reading from a CD till the reading from a CD, this whole process may be considered as a communication system. And what are the different type of sources that we come across in digital communication? In digital communication, the data that is to be transmitted is in the digital form. There are different types of sources in reality, but in digital communication the source has to be converted to a digital form. The source to start with may not be digital, may be digital or may not be digital. If it is digital, there is nothing to be done. If it is not digital, then it needs to be converted to a digital form. So, there are two types of source and they are digital source and analog source. A digital source may be of different kinds. For example, it may be binary source like a binary file in a computer, and that has many bits. So, it is a sequence of bits. So, when you want to transmit such a file, it is basically that we want to transmit some bits in sequence. And there are other type of digital sources which are not binary in nature. For example, when we are typing and we are basically typing English text. So, that English text is also implicitly a digital signal, because every character can be one of the finite set of characters. So, it may be one of the 26 alphabets, capital letters, small letters. So, there are 52, there are numerical characters, there are punctuation marks and so on. So, in total there are finite number of characters that we would like to transmit, that the English text has. So, this is also a digital signal. So, a digital signal is characterized by the fact that every point, every sample can take only finite number of values, unlike an analog source where every sample is at every point the value may be one of the infinite number of values. So, for example, it may be a real number which has infinite possibilities. So, English text is an example of a digital source, digital signal, and however, though it is not binary in nature, it can still be converted to a binary signal by using some form of binary code for every character. So, for example, ASCII code is one very popular standard for representing the English characters in the form of binary strings. So, every letter or every character is represented by 8 bits in this code. So, by using this code we can convert any English text, for example, a whole book in English, into binary form. So, we can convert it into a binary file. Okay. So, to summarize, we have any digital source represented in the form of binary strings. We can represent any digital source in the form of binary sequence. Now, there are also analog sources in nature. For example, the audio signal that we capture from microphone is basically an analog signal. It is continuous in time and also it is continuous valued, meaning by at any point of time the voltage level that is generated at the microphone can have infinite possibilities. It is a real number. Similarly, the video signal that is captured in a video camera has infinite possibilities for the color at every point, or infinite possibilities for the gray level at every point. So, it is basically an analog signal. It is continuous valued signal and also it is continuous time in nature. There are, even if we have 1 second duration of audio or video signal, there are infinitely many samples in that 1 second duration. So, it is continuous in time as well as it is continuous valued signal. So, analog sources are continuous time and continuous valued. Now, we have just now said that in a digital communication system the source has to be represented in the digital form, and then we will use digital techniques to transmit the digital data. So, analog signal also has to be converted into digital form for us to be able to use digital communication systems to transmit that signal. So, the common block that is used in this purpose is called the A to D converter, which is the abbreviation for analog to digital converter, and this usually involves 2 operations, and we will come to that in a moment. So, they are basically sampling and quantization, and we will come to that in a moment. Okay, so, we have discussed source to some details. Now, let us see what kind of channels we usually see in practice. So, the common examples of channels are wireline channels, like that is there in telephone, fiber optic cable, space, where for example mobile cellular phones operate, satellite communications use space as channel, storage channel. Just now we discussed about magnetic recording channels, they are basically storage channels, or CD, optical recording channels, CD, then magnetic tape, etc. And there is also underwater acoustic channel, where the signal is transmitted from one point in under sea to another point under the sea. So, the signal goes through the water. So, that is little different from the space. Okay. Now, these channels, if they behaved in a deterministic manner, for example, what we mean by that is that if we knew exactly how the channel will change the signal when we transmit the signal, then our job will be quite simple. We would like to get the transmitted signal back. So, the job of the receiver now is just to invert the process of the channel. So, we need to design an inverse system, so that will solve the problem. But in practice the channels do not behave in a deterministic manner, and that gives rise to all the problems, and that is actually why we need to study so much and do so much about digital communication. And the channels are not deterministic, and they are most of the times why they are deterministic, they are not deterministic, is that there is noise in the channel. So, the noise may be introduced from the channel or it may be in the receiver. So, there are different kind of noise, the noise themselves may be different kind of noise, may be either man-made noise, or they may be generated in the natural processes like lightning and so on, or man-made noises like switching also generate noise. Now, there are different kind of noises in nature: thermal noise, flicker noise, impulse noise. These are just few different types of noise. Though there are these different types of noise, the most predominant type of noise that we come across in communication systems is the thermal noise. And this thermal noise, though as we said noise is random in nature, there is no way to predict exactly what value the noise will take at any point of time. So, does it mean that we do not have any information about the noise? No, we do have some information about the noise. Usually we assume that we know the statistics of the noise, and that usually can be estimated by performing experiments. Or there are models for the noise that are reasonably good in practice. So, they reasonably well approximates the noise that we come across in practice. And thermal noise is usually modeled as Gaussian noise. And the most common type of channel as a result that we come across in communication systems is what is known as additive white Gaussian noise channel, or that is abbreviated as AWGN channel. In this channel model, the transmitted signal goes through a deterministic change in the channel, and then a Gaussian noise is added. So, this is basically the thermal noise that is generated at different electronic devices in the receiver. So, the thermal noise is modeled as Gaussian noise, and it is added to the signal that we get after it goes through the deterministic change. So, the received signal is the transmitted signal changed deterministically plus a Gaussian noise, and usually this Gaussian noise is assumed to be white, and what it means is that the noise is uncorrelated. That means at one point of time the noise value that we see has no correlation with at any other point of time whatever noise value we see. So, two different noise samples at different time instances do not have any correlation. That is what white noise means. We will see more about this white noise in a later class when we discuss some background material about probability and random process. Okay, so though we know that most of the early communication systems are analog in nature, for example radio, television and telephone, one of the earliest communication systems was digital in nature, and that is the telegraph system. It was a very nice and efficient digital communication system which actually had lot of advanced ideas in it. And there the purpose was to transmit English text, and as we discussed some time back, the English text is not a binary signal in nature. So they have, so this famous code called Morse code actually encodes these characters A to Z, there are 26 of them, 0 to 9 the numerical characters, and these 3 punctuation marks, and they are expressed as sequences of dots, dashes and space. And there was a nice system designed to transmit English text using this code. So A has a particular sequence of dots and dashes, and similarly all the other characters, and at the transmitter end, if an English text is to be transmitted, every letter will be coded individually using this Morse code, and they will be transmitted by dots and dashes. So in this case, dot usually means a short pulse, short duration pulse of electrical signal. So short electrical pulse of current, and a dash will mean a longer duration electrical pulse. So, and the space is a gap between gap when there is no signal transmitted. So in this form there is an interesting instrument where, so this was the one of the earliest instruments that was used to generate the electrical pulses. In this there is a key here which can be pressed to make contact between two metallic parts, and when you press it there will be a contact, and then there will be current flowing through the wires that go to the other end of the to another telegraph center, and this can be pressed for a shorter duration or a longer duration by the operator, and those operators used to be called sounders, because when this switch is pressed it makes a clicking sound. So tick tick sound is made by this key when it is pressed. So the sounders will actually encode the English text, and they usually know the whole Morse code by heart. So they can encode any English text really very fast. And at the other end of the at the receiving station there will be also receiving operators who will actually hear the pulse coming, in the sense that the pulses that come, the electrical currents that come, they will be used to generate some sounds of shorter or longer duration at the receiving station, and the receiving operator, who will be a person, he will hear the signal that is coming, and he will immediately write down the message after decoding. So these receiving operators will be trained people, they will be trained on Morse code just like a language. So they will learn Morse code as a language, so that they can hear any signal in Morse code and they can decipher in running time. So this telegraph key, this kind of telegraph key was used for a long time to transmit English text through telegraph. And in the Morse code there are some very interesting ideas used, which even nowadays advanced techniques use. So the idea is that all the letters and all the characters that were encoded were not encoded by same number of dots and dashes. The number of dots and dashes that will be used to represent a character was kind of inversely proportional to the frequency in which those characters come in English text. So frequent characters will be represented by shorter sequences of dots and dashes, and the rare characters like Z and punctuation marks like interrogation marks, they will be represented by long sequences of dots and dashes, so that on average if we see an English text represented by Morse code, it will have a minimum length. So that is what is desired, because we do not want to take a lot of time to transmit a message. So for that, the characters which are more frequent, so they need to be transmitted more in number, so they will be represented by smaller number of dots and dashes, and the rare characters like Z will be represented by longer sequences of dots and dashes. So the purpose is to minimize the average length of the code strings. So when we discuss source coding in a later point of time in this course, we will see that that is the basic idea that is used in source coding. To minimize the average length of code strings, we try to assign longer sequences of bits to the rare characters or rare symbols and shorter sequences of bits to the frequent characters. And here is an example of some Morse code for some of the letters, some of the characters. This is not really the original Morse code. Original Morse code had some spaces in it, and later on when manual transmission and reception was ruled out and it was automated, it was found that this space is difficult to, due to this space the Morse code is difficult to implement in an automatic way. So it is not perfectly binary in nature. So this space character was removed and another Morse code which is called International Morse code was developed for this purpose, and here space character was not used. So here we see that in this example E is represented by a single dot, Z is dash dash dot dot, 1 is dot dash 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 4 dashes, and interrogation mark is dot dot dash dash dot dot. So here we see that the character E has only one dot, it is encoded by a single dot. So the purpose is quite obvious, because E is the most frequent letter in English text, in English language. So if E is represented by a short sequence, the shortest possible, then we will save a lot of time in encoding English text, because E needs to be encoded many times. And then on the other hand, Z has very, it comes in English text very rarely, its frequency is very less. So as a result, we want to encode Z by a longer sequence. There is no harm if we encode Z by a longer sequence than other more frequent letters. So that is what is done, and the numerical characters are even less frequent in English text, and that is why the numerical characters are encoded by longer sequences. In fact, all numerical characters are encoded by five symbols in this International Morse code, and this interrogation mark this type of punctuation marks are encoded by 6 characters, 6 dots and dashes. Okay. So, we see that one of the earliest communication system was a digital communication system, and it used a very fantastic idea about encoding English text into a binary form, dots and dashes. So, we can say that dots are just zeros and dashes are just ones, and say that this is a binary encoding of the English text. And the Morse code also has the basic idea of source coding that we will see in detail in a later class. Now, let us see what a digital communication system has, the basic digital communication system has today. We have a digital source. The output of this digital source is some kind of digital signal, though in most of the course we will assume that the digital source generates binary signals, and that assumption is not really a lot of restriction, because it is not a strong assumption, because we are dealing with digital source, and a digital signal can always be represented by binary sequence. So, by using ASCII code we encode English text, or by Morse code. So, digital source, there is no harm in assuming that the digital source is a binary source. And then there is a source encoder which tries to compress the data that it is receiving from the digital source into minimum number of bits, because we do not want to use a lot of bandwidth in this channel to transmit the same amount of data. So, there is different reason for which the source may be generating redundant information. So, the 100 bits here may not contain really the maximum amount of information that 100 bits can carry. So, as a result, there may be scope for compression of the source, and we know that we can compress a binary file, for example, to a great extent by using different compression softwares like Gunzip and so on. So, those are basically source encoders. Those softwares implement some source coding techniques, and the reason why there may be some redundancy in the output of the digital source is that, first of all, there may be the zeros and ones here, if it is binary signal, may not be equiparable. So, there may be more zeros than ones on average here. So, for example, if there are 90% of the bits are zeros, then obviously they do not carry so much information, because at the other end most of the times we can guess that the bit will be 0 than 1. So, the 0 does not carry so much information. So, there would possibly be a way of compressing the output of the source if the source is of that type, if the source generates bits where 0 and 1 are not equiparable. Another reason why there may be redundancy in the source output is that there may be correlation between the consecutive bits. So, for example, in an image signal, if one pixel is blue, if it is a blue pixel, then the probability that the next pixel is also blue pixel is very high. Usually the neighboring pixels have similar color. So, in an image signal there is high correlation between neighboring pixels, and as a result we can say that all the pixels do not carry really independent information. If we know one pixel value, there is no need to transmit equal number of bits for transmitting the next pixel. So, there is possibly way of transmitting some difference between the pixel, for example, which will require less number of bits. So, the reason why there may be scope for compression of the digital source is that either the source signal may not be, the signal samples may not be independent of each other, there may be correlation, or the signal values may not be equiparable. Then the next block is the channel encoder, where it receives some bits here and then it tries to transmit the signal in a way that is suitable for the channel. And so it takes care of what kind of channel the system has, and then it tries to shape the signal in a way so that the receiver will be able to get the maximum information from what it receives. So, a very traditional way of doing channel encoding is to do error correction coding, where if we have k number of bits to be transmitted, we actually transmit few more bits, add few more bits, but they are not extra information bits, but those bits are actually derived from the k number of bits that we want to transmit. And so those bits do not carry any extra information, they are redundant bits, but those bits enable the receiver to correct some bits if the channel introduces some error. If the channel introduces some errors, that is flip some bits, then the receiver will be able to correct to some extent the bits that are in wrong. And the next is digital modulator, which is specially used for analog channels. Most of the channels are analog in nature, and so we want to transmit digital signal. So this the input is digital, but the output of the digital modulator is an analog signal. So this is the interface between the digital part and the analog channel. Okay, now the receiver, so this part is the transmitter and here is the receiver, and in the receiver the counterparts of these blocks are there in the opposite sequence. First there is a digital modulator here at the front end of the transmitter. So here we have to demodulate the signal that is coming from the channel that we are receiving. So this digital demodulator you will receive the analog signal and try to estimate what value was transmitted here. So if it is binary, it will try to estimate what is the bit that was transmitted here from the waveform it receives. So its output will be bits, and then the channel decoder will try to correct some errors if there are some errors in the detection here. So channel might have introduced some distortion in the analog signal, due to which the digital demodulator detected some bits wrongly. So if the digital demodulator detected some bits wrongly, then the channel decoder will be able to correct those bits with the help of the extra information bits that were transmitted by the channel encoder. So that will be possible, that the channel decoder will be able to do to some extent, not that whatever is the number of errors that the channel introduces or the digital demodulator introduces, the channel decoder will be able to correct. It will be able to correct, say, maybe up to 2 bits in error or 3 bits in error, that depends on the design of the system. And so we have to see that we have to note that if we choose to correct more and more errors, we need to add more and more redundant bits. So as a result, we need to compromise on the rate of transmission. So we will discuss this in detail in a later class in the course. And the channel decoder then gives its output to the source decoder, which take this signal and then reproduces the signal that the source generated. So this is the output signal at the receiver. Now though the digital source is assumed in this block diagram, the source in practice may not be digital, as we said. So in that case we need to convert the analog signal coming out of the analog source to a digital form, and that involves two operations. One is the sampling and the other is the quantization and coding. So, the analog source needs to be digitized by sampling and quantization. So, if we have an analog source to start with, we need to do A to D converter, analog to digital conversion, and that involves sampling and quantization and coding. So, quantization, so what does sampling do? Sampling basically, so the analog source is generating a signal which is continuous time, but we cannot transmit the signal at all time instances because there are infinite number of time instances even in 1 second duration of signal. So, we need to discretize the signal in time. We cannot transmit the signal value at every time instant. So, we will be, so what is done usually is that we cut the time instances into some points in regular intervals, and then we take the values of the signal only at those regular time intervals and then transmit the signal value at those time instances. So, that is the job of the sampler, and we will discuss in detail the sampling in detail in a later class. And the next step that is done is quantization and coding. So, in quantization, each sample value is still analog. In quantization, we like to discretize the amplitude also. So, here only finite number of values will be taken as representative values, and then when we see that the sample has a particular value, we try to see what is the nearest representative value that we have chosen, and we will only like to transmit that representative value, not the exact value of the sample, because to transmit the exact value of the sample we need infinite number of bits. So, we choose only finite number of representative values in a certain range. So, we have some representative values of the sample, and then we have a particular value of the sample and we choose the nearest level or the representative value, and we encode that, we represent that level with some bits. Remember that we have only finite number of levels now. So, if there are 8 levels, for example, we can assign 3 bits to each level, 3 distinct bits to each level, and then corresponding to the level that is nearest to the sample value, we have those 3 bits, and those 3 bits is the encoded string for the sample. And of course, in this process there is some error, because the level is not the actual value of the sample, but it is an approximation. So, there is no way of getting the exact sample value back from the quantized sample. There is some loss of information, but most of the times that we would like to quantize with a sufficient number of bits, that is in a sufficient number of levels, so that the quantization noise, the error is small enough in our, that is, it is in our toleration level. Okay. So, once we have this A to D converter, the analog source and the A to D converter together can be considered as a digital source, and then it fits perfectly in our previous digital communication system. So, this digital source, now if the actual source in the system is analog, this digital source is actually the source that is shown here. It is actually an analog source together with an A to D converter. This output is a digital signal. Okay. So, though in this main block diagram we have shown channel encoder and digital modulator separately, in most modern communication systems this channel encoder has 2 parts. and this demodulator, this digital modulator is usually combined with some coding, and that block is called coded modulator. So there is something called coded modulation which combines coding and modulation together to get better performance. And the of course there is still a channel encoder kept, usually still a separate channel encoder used for further error correction. So in many systems today, the block diagram that is useful is this. There is an encoder and then there is coded modulator block. This encoder is channel encoder, but there is also some coding here which is combined with the modulation. Okay, now we have discussed the digital communication system to some extent, but why do digital communication at all, especially when the source is analog? Why do we want to convert it to digital and then transmit using digital communication systems? Most early communication systems that use that transmit analog information is analog in nature. AM, FM radio, television, telephone system, everything was analog communication. So why do we do digital communication? Today almost every system, every new system that we design is a digital communication system. For example, cellular, mobile, internet, communication, local area network, everything is digital in nature. So why is it that we communicate using digital communication techniques even if the source is analog in nature? The reason is that first of all, the digital communication technology has developed to a great extent and the technology is very advanced today. So when we want to implement a digital communication system, it is often much cheaper and easier to design than analog communication system, because the digital electronics has become very cheap and easy to design, and they are also very easy to design because there are many digital electronic devices are programmable in nature. So as a result, they are often very easy to design. And also with the advanced digital communication technology that we have today, we can achieve near capacity rates. So in other words, for every channel there is a maximum rate at which we can communicate, that is called the capacity of the channel. And the today's digital communication technology has gone to such an advancement that we can achieve almost that rates near capacity. So digital communication becomes almost the obvious choice when we want to implement a new communication system today. Now in a communication system, we need to know very clearly what are the constraints that we have and what are the resources we have. So the resources we have is the channel is of course the main resource that we have. We need to transmit whatever signal we have through the channel. So how much is the capability of the channel? That is a fundamental question. And how much information can be transmitted through the channel most of the times depends on the spectrum that is available. The spectrum available in a channel is limited in practice, and that is because of mainly two reasons. One is that the channel frequency response itself may be limited. The channel may have very high attenuation outside some particular bandwidth, and as a result we have to transmit our signal only in that band where the channel response is good enough. And second, whatever bandwidth the channel has, that also may not be available to us for a particular application and for a particular user, because it may be shared by different users and or different applications. For example, in a cellular mobile system, the spectrum available is actually large, but then a particular service provider, for example BSNL, has a particular bandwidth assigned that they can use for this purpose. They cannot go outside that band, because the other bands are used by other service providers or other applications. There is military application, there is police application, there is medical application, there is numerous applications that use wireless media for communication. So because of so many applications, so many users using the wireless channel, the spectrum that is available for a particular user for a particular application is limited. And even for the users using the BSNL service, they have to share the same spectrum that is allocated to BSNL. So BSNL will now allocate different spectrum either in frequency domain, or of course they can do it in time domain. They can allocate also different time. So in any case, the resource will be allocated to different users and to different applications in practice. So that is the reason why the spectrum available to a particular user for a particular application is often limited. The next resource that is available to us, which is also very crucial, is the transmitted power. And the transmitted power is also limited in nature, limited in practice. The reason for that is, first, the constraint on battery power. Many communication systems, many transmitters operate on battery power. For example, mobile phone, there is a battery which needs to be recharged periodically. So if we transmit a lot of power, then the battery will be drained too fast, and then we need to recharge the battery more frequently, and that is not desired. So as a result, we need to design systems which use less transmitted power. So that is one reason why the transmitted power is constrained. And the second reason is interference. Consider the wireless application, wireless communication application, where the media is actually common for many applications and for many users. For example, in a particular cell, the mobile, I have a mobile which is transmitting some signal in a particular cell. I am in a particular cell. Now in another cell, maybe some distance away from my cell, there are other users who are using the same frequency. So if I transmit a lot of power in the same frequency, then the users in the other cell who are using the same frequency will be interfered by my signal. So the transmitted signal power that is transmitted by my mobile phone needs to be limited to avoid interference with other phones. So transmitted power is limited because of battery power limitation and also because of interference to other users and applications. And one crucial parameter, channel parameter that will play a very important role in the course is in a communication system is the noise variance. The noise variance, we can of course intuitively feel that if the channel has more noise, we cannot transmit a lot of information, because the channel is distorting to a high extent. Channel distortion is high. So of course we can argue that there is if the noise variance is high, we can always attenuate the signal received at the output of the channel at the receiver, and then the noise variance at the output of the attenuator will be less. We can attenuate the noise, but then if we attenuate the received signal, the transmitted signal that is coming with the received signal is also attenuated. So that does not help either. Both the transmitted signal and the noise are attenuated by the same factor. So that does not help. So when we talk about noise variance, what we assume is that the channel attenuation is 1. There is no channel attenuation. So if there is channel attenuation, we can amplify the received signal so that the overall channel and the amplifier together has a gain 1, and then we can talk about the noise variance at the output of the amplifier. Amplifier will also amplify the noise. So when we normalize the channel gain, what is the noise variance? That is what matters to us. That will also dictate what is the signal to noise ratio at the receiver. If we amplify the received signal, the signal to noise ratio does not change. So, but of course SNR is not only dependent on the noise variance, it also depends on what was transmitted, what energy was transmitted by the transmitter. If the transmitted energy is more, the SNR will also be more. So so noise variance on the other hand is a parameter which depends only on the, which is included only in the channel model. Though we say that this is a noise introduced by the channel, we have to strictly remember that most of the noise, especially the Gaussian noise, that is the thermal noise, is not introduced by the channel, but it is generated at the receiver. It is generated in the devices, electronic devices in the receiver. So it is actually, it is often called receiver noise instead of channel noise. Okay, so we will discuss the topics that we have seen in the block diagram of a digital communication system in detail in this course, and there are plenty of textbooks available for digital communication. As we go on for different topics, I will keep suggesting different textbooks which you can refer, and to start with, you can refer Digital Communications by Prokis. That is a fairly good textbook, and we will come across other books, and I will refer other books in the due course as we go on. Thank you.